Revolution in engineering education, I love it.
Yeah.
And then these other ones, meaningful, consequential work, inclusive culture. I seldom see a introductory slide that gets me, like I want to listen to this. That's a really nice introductory slide.
I hope I don't disappoint you.
High initial expectations.
Yeah, I know.
I think you'll do great.
Pressure.
I actually met Susan. We had a nice conversation about 4 months ago.
Yeah.
And I thought, like, wow, this she'd be great to come and talk to us about these issues. So that's why Susan is here. I first thought it would be great for her to come from Seattle and see the winter here in Michigan. But apparently it's as wintry in Seattle as it is in Michigan right now. So
we currently have more snow than you do.
Yeah.
So, yes.
Yeah. I was asked, a couple of people asked me, where are the videos for these presentations? Where are they published? It's a really good question. Susan would like to know. Someone else asked me. I asked Chris. Chris, everyone know Chris? This is Chris. So if you can't find your video, it's Chris that you have to talk to. But apparently, if you go back to your page where your presentation is announced, there should be a link to your presentation.
Even better, it will be embedded into the page. So
yeah, it's embedded.
I have a page?
You have a page that announces who you are and write a little picture of you and your little description and et cetera, et cetera.
Somebody will show me where this page is and then I'll know where to find it.
Yes. Yeah. Well, you vote for Create for STEM, you can find it pretty easily.
Okay. Okay, good.
Great. Well, I talk too much as it is, and I really want to have Susan talk to us. It's traditional, just like we've always done in the past. She'll give a little presentation, and then we'll have a nice discussion following that.
Yeah.
So thank you for coming. It's a long, it seems like continental USA, but for those of you who've ever traveled between here and Seattle, it is a long, and that 3 hours, at least for me, disrupts me. So thank you very much. I'm very appreciative.
Yeah. Well, thank you. Okay. Yay. All right. Hi, everybody. Thank you so much for coming out on a wintry day, although that's probably most days here, so maybe it's not all that unusual. So I'm going to talk a little bit about a project that we've been doing. The title slide kind of says it all, Revolution in Engineering Education. And that graphic is actually one that I created on my little tablet when I was at a PI meeting with my team, and we were trying to figure out a different visual representation of what we were trying to do, and we collectively came up with that. So I'll explain how that works in a second. So I work with folks in the School of Chemical, Biological, and Environmental Engineering at Oregon State University, even though I am a Husky from University of Washington. I will use the acronym CBEE through this talk. That's what it refers to. Essentially, it's a school, but it functions like a department. It's about 32 faculty members. And we put in some years ago now for a RED grant from NSF. RED was Revolutionizing Engineering Departments. It's now Engineering and Computer Science Departments. And what we stated our project goal was to seek revolutionary change in the CBE school through construction of a culture of inclusion and a shift in our learning environments from sequestered activities to meaningful consequential work. And we came up with a graphic in about the second year of the project. We had this thing with pillars, and it was like silos. It was bad, just like the different pieces of our project, and we didn't talk to each other. It was bad. This is much better because it really captures what we think we're doing. So working on inclusive culture includes and informs and co-constitutes the meaningful consequential work that students do in classrooms, which then also feeds into the inclusive culture. So I'll show you how that works in a piece of the project in a little bit. So I just wanted to say a few words about the evolution of our revolution. We responded to the RED RFP in its initial year. We were part of the initial cohort of 10 sites. There are now 30 sites across the country, different sizes of school, from large land grants like OSU to small privates, and everything in between, community college. And they provided us gratefully with funding and a national community of people who are also working on similar kinds of projects. We meet annually as a group. And then the initial work by the CBEE Red team at Oregon State then led to where we are now, which is we're trying to institutionalize the practices and structures that we've helped to create to try to make it an ongoing CBEE project and not the Red project. So we're trying to shift that and having some success. Our initial pitch to NSF was through this lovely graphic, which they liked. I love it. But this tried to show how we were conceptualizing the space in which we wanted to do this work. And part of it relates to the problems of the way CBEE was initially. So what we see in engineering education is that engineering ed happens mostly in colleges and universities, but it also tries to relate to and sometimes happens in part in industry and nonprofits and other places where engineers do their work. And really, engineering education should happen at the nexus between those two larger kinds of communities. And then within that space of engineering education, you also get tensions and connections in the system between the curriculum, the pedagogy, the students, the kinds of co-curricular activities that they're used to, the faculty and the GTAs and their ideas and practices and so forth. And all of these things are in tension with each other. So if you want to make revolutionary change, we argued, you've got to keep the system in mind and try to figure out how to leverage those tensions to make them productive. So we use we draw on several different versions of activity systems, activity theory as our theory of change in that way. We have this co-constitution, isn't that a great word? I just made it up, of meaningful consequential work and inclusive culture that inform each other in interesting ways. And that has led us to a variety of changes, which I'm going to just dash through very quickly for you here, and we'll focus on one later. So we're in year 4 of a 5-year grant. We've made some changes in curriculum and instruction. They've been working towards vertical integration of the courses, which was really novel for them to do. They had the kind of standard engineering ed collection of topics. Each topic gets a course. They're in a rough order because that's the way we've always done it, and so does everybody else kind of thing, to actually trying to think about how to integrate the courses vertically so that the students see connections between the courses at different levels. That has involved trying to, in the community, this doesn't happen on the red team, this happens in the faculty of the department, identifying components of disciplinary knowledge that then can help with that integration. And also we've been working on what we're going to call Studio 2.0, which is to try to change the activity that happens in studio classes, which are small groups or working in sections of large lecture classes on problems, trying to change those to make them more meaningful and consequential and inclusive. We've also done some changing of the departmental culture because we're interested in the culture not only for students but for faculty. They have a thing at Oregon State where they have position descriptions that are negotiable. So you get hired, right? You get a position description when you get hired. You're all familiar with that. But every year they have an opportunity to renegotiate the things that they're supposed to be held responsible for merit and promotion and so forth. And so that has shifted to include valuing work on inclusivity within the department, both for faculty and for students. They've also been trying to work on better supporting their fairly large group of international students who, it was very clear from our early data collection, were kind of left to the side. People didn't understand how to work with them well. It was an issue. Everybody understood it, but nobody was actually doing anything about it. So we're trying to get some traction on that. Changing various policies, norms, and practices for workplace equity, and some pretty significant faculty professional development around power, privilege, and inclusion. including a 60-hour summer workshop that about half the faculty have completed, which is pretty amazing. Then we've also tried to kind of, at the boundary there between culture and instruction, we've worked on developing a school-wide vision of inclusive teaming practices for students when they work in groups. We've developed a small grants program called Teaching Innovation Fellows, where we give a small amount of money and a little bit of time to faculty who want to work on implementing some new teaching innovations in their classes. They have started this year having what they call Teaching 10. Every faculty meeting, they spend 10 minutes talking about some problem of teaching practice, which immediately evoked a response by the now newly appointed school head that they needed to have a research 10 too. So the research folks didn't feel left out. We all kind of rolled our eyes and said, okay, let's be inclusive. And this cool thing called alternating leads. So one of the problems with doing change in instruction in a research-intensive place like Oregon State is that people don't have time to do it, and bandwidth, and they might not have a skill set, and they might not know enough about a particular course to do that they're taking on. So the alternating leads, we just started this year. It was approved, and 2 faculty get appointed to a course. 1 faculty is in charge of delivering the course. The other faculty is involved with creating the instructional activities and kibitzing with the instructor, the person who's taking the lead that year, to try to make connections between what happens in lecture, what happens in studio, what happens in homework, and so forth. So it gives everybody a little bit more time and a built-in collaboration team to do that work with. And then the following year, they flip. The person who was the instructional designer person now delivers the course, and the person who delivered the course now is the instructional designer, and it continues on. So at least for 2 years, and maybe beyond that if it works and people like it. So those are some of the things that we've done in the first 4 years that we're trying to get institutionalized in CBEE. So it's a design-based research project, and that means that we feed the data back into the design of the activities that are happening. So we've collected data in a number of ways, including faculty interviews and looking at de-identified changed position descriptions to see how that's working out. We have instituted an annual student climate survey that's pretty extensive. And I'm happy to talk to anybody who's interested about the construction of that. We've found some interesting things like if you ask students about the climate for different groups, they differentiate even if it's not their group. So, and I'll tell you more about that if you want to know. We've also, they've had some international student listening sessions that were conducted by international faculty to talk with international students about what they need and what they'd like to see in terms of support. That's progressing. They've been doing some work to try to highlight the work of international students and their contribution to the school in a more public space. We've done exit interviews with graduating students as part of the ABET process. We've done student focus groups, and we've collected ethnographic data as people work on all of these different aspects of the project. We've also worked on instruction. We've got a sort of a Studio 2.0 community of practice. Again, I'm not going to go into detail about the community of practice end of that, but if you're interested, I'm happy to chat. We've collected data from the curriculum committee documents as they revise the curriculum. And we've done video studies of Studio 2.0, which is what I'm going to focus on when we go into kind of the deep dive part of the talk. So, curriculum reform, we draw on, as we think about how to reform the curriculum and the instructional practices in CBEE, we used Dorothy Holland's and colleagues' notion of figured worlds, and we talk about the figured worlds of engineering education. And each figured world, which I'll explain in a minute, has its own practices, its own norms for interaction and other things, its own values, and its own identities and roles for the people who inhabit that particular world. So when we think about, normally when we think about post-secondary curriculum, it lives in school world. And in school world, there's norms for how you do work in school, what's valued in school, how you do, for example, small group interactions in school, what kinds of things you study in school, how those things are or are not connected. And the curriculum lives in school world. And what we think is, if in most, in the way CBE, I won't even say most, in the way CBE was organized, it was largely engineering world is out there. They go to engineering world with their toolkit that they've learned in school world, and then they're suddenly engineers. And then we get information back from the industry folks who say, we have to reteach them a whole bunch of stuff when they get here, which is a problem that we will return to. And so in order to make the work that they do in school more meaningful and consequential, we figured we need to bring these two worlds together and to try to situate or resituate the curriculum in the overlap between engineering world and school world. So one of the ways we've done that is through this thing that we'll call Studio 2.0. But there were things that were going on in CBE before we got the Red Grant. So we didn't like start from nothing and suddenly create all this stuff. We built on what was going on already. So there was already a move to incorporate more active learning practices, including things like clicker, questions and lectures and things like that, and including what they call studio sections for large lecture courses. So the courses we're talking about in CBEE are really anywhere from 100 to 250 students, depending on the course and the year. And each one of those then is broken up. They go to lecture twice a week usually, and then once or twice a week they go to a studio section where they're with about 30 of their colleagues and they work in small groups on problems. And so the problems were kind of the problem that we started with here. Like, what are we asking them to do in studio? And what was happening was they were being asked to do primarily typical engineering school kinds of back-of-the-book homework problem tasks. They tended to be decontextualized or only lightly, like with a little cover story kind of contextualized. And to have algorithmic solution paths, and there's usually a single solution path that was preferred and a single right answer. And so that called on practices that were learned as part of school world, and those practices of doing the engineering stuff get learned in association with school world practices. Not engineering world, but school world. This can lead to difficulty in using those concepts to reason or debate or to critically examine approaches and designs, and also to lack of transfer to engineering contexts. And the other thing that we noticed about what was going on was that group work often tends to be dominated by one or two people. They tend to have high status in school world and be good students. And so efficient group work often looks like one student talking or maybe two students talking a little bit, and other students writing and nodding, and occasionally interjecting something like, yeah. Right? Not exactly what we think about as really serious group work. So that was Studio 1.0, and now I'm going to tell you about the differences between that and Studio 2.0 design. So this reform was in 11 core courses, the engineering science courses, in CBE, to try to move students from doing the kind of worksheeting, fill out the blank, get the right answer activity that we saw in Studio 1.0 to more group-worthy tasks that are complex enough to benefit from multiple perspectives, and so encourage more inclusive activity and understanding. And we drew on the work of those fine folks, Cohen and Lotan, Engel et al. In several dimensions, Lonnie Horn, David Hammer, Andrew Pickering, and so forth. So we looked at, you can think about these two ways of doing studio design along some different dimensions that I'll just pull out to highlight here that are related to this idea of the two worlds of school world and engineering world. So in those two worlds, the identities and activity and norms were different. We talked about that. And so what we see in 1.0 is decontextualized problems with a final answer and a single solution path. We also see limited opportunity for students to express creativity and problem-solving skills. The authority tends to lie in the instructor. And we see that when we analyze the discourse because students refer to they when they talk about the instructor. Like they want us to do this, they say we should do that, they won't let us do this. Or it, the worksheet as the extension of the instruction. It says to do this or whatever. When they talk in Studio 2.0, it looks different. So in Studio 2.0, we're asking students to be professional engineers or to masquerade as them, tackling more open-ended problems, as opposed to asking them to be students. We're asking them to be engineers. And they're encouraged to work with their group to come up with their own approach. The authority rests in the student within the engineering norms, within the disciplinary norms. So we're holding them accountable to engineering norms, but they get a lot of latitude to figure out how to approach these problems within those norms. And when we look at the discourse there, they tend to use the pronoun we. We need to do this, we should do that, we haven't thought about this other thing, as opposed to it and they. The framing of these in Studio 1.0 is bounded. It's either not mentioned at all, do this task, or it's framed in a very bounded kind of a way. This is a problem that you're going to do in this chapter on this topic. Expansive framing, this is Randy Engel's work, tries to draw on the connections between the activity and the world that these folks are supposed to be preparing to enter, engineering world. And the moves are involved. This is from Pickering's work, who argued that science, the work of science, and we've argued the work of engineering, is a combination of, when you're working, free moves and forced moves. The free moves are where you have the opportunity to think in new ways or combine things in new ways or come at problems from various angles. Forced moves are the disciplinary practices that you're held accountable to because you're doing work in a discipline. So that's the work of science and the work of engineering. But in school world, what you mostly see in these Studio 1.0 activities is mostly forced moves. A lot of times these actually look very recipe-like. First do this, then do that, then do this other thing. There's very little room for movement. But we have to think about the problems associated with this, and because we've been trying to talk folks into using these kinds of studio activities, and we've received some resistance, we have started to think about what the source of the resistance is. So open-ended contextualized problems are risky in that they tend to increase student uncertainty and confusion. That we have showed videotapes of students who are deeply into engineering world in these practices. We were very excited. Oh, look, they're being engineers. Isn't that cool? And the response from some faculty members is they're confused. Why don't they know how to do this? They should know that by now. And what they're looking for is a very smooth, error-free solution of standard problems. So it's risky. Engineering school and maybe even post-secondary norms say good teaching is clear explanations. If I give clear explanations, I'm a good teacher, and that leads to students who know how to solve our problems. Right? If that's your idea of good teaching in post-secondary school, this is not going to feel very comfortable. So confusion in students then gets taken as a sign of poor teaching or poor learning. So the students are lazy, they didn't do the reading, they didn't do their homework. They're just not interested, they don't care. Confusion is bad, confusion is scary. We don't want confusion. So we thought, well, we should look at this because we think confusion can be really productive in some ways. So another reason that they might resist change is that they have this model of constrained tasks that works well with their way of thinking about post-secondary education and their role as teachers. So when procedures are clear, there is less student confusion. resources are localized to the specific course content in which you're working, and so they can focus their resource out so they're not looking all over the internet trying to figure out how to do something. And if everybody's using the same approach when you're running small groups, it's easy to monitor. You can walk around and see if they're making a mistake or not. If they're confused, they raise your hand, you come and explain it again, and they go off, and it sounds way more comfortable. So there's less uncertainty for both the student, they're happy, and the instructor. And if you're using, as in a lot of the studio courses at OSU use TAs and learning assistants, they're easier to train and more comfortable because all you have to do is say, here's the correct answer, walk around and check and make sure that they got it. All right, so there's a lot of, I want to say, there's a lot of pressure to keep things the way they are, and a lot of resistance, therefore, to changing it anyway. So we did some studies. We started out with lab studies where we brought students in and gave them tasks that were written for courses that they had recently completed, just to see what they would do with those tasks. And our research question in this set of studies is, how do student teams take up an engineering task designed for them to adopt roles reflective of professional engineers? Because if students are resisting them, we should be able to see that. And if they're not resisting them, or it's mixed, we should be able to try to figure out the dynamics that are happening with that. And then in the study I'm going to talk about in a minute, this is work with Ed Mykor and Milo Koretsky. It'll be presented at ASCE this year in a paper called Destigmatizing Confusion. Our research questions was the same research question I just gave you, plus in what ways might confusion be a productive state of engagement toward forming engineers? So what do we get out of letting them be confused? And the idea behind this was, if we can point to ways in which confusion is good, maybe we can convince our colleagues that they should let it happen a little more often. All right, so here's the case of confusion I'm going to show you. It's a group of 6 second-year students in CBEE. It's the 7th week in a quarter-long course on material balances. So they're well and truly into the course. They've had some tests. They've done studios every week. There's a graduate teaching assistant, and there's an undergraduate learning assistant facilitating the group work. And here's the task that they're working on. This task is different from other tasks. They've been doing a diet of mostly Studio 1.0 tasks, the more constrained school world tasks. And then this task gets given to them, and the framing is basically, here's something really different. So it was designed by the instructor of the course, who was not on our research team, using design principles from problem-based learning and model eliciting activities. The students are situated as process engineers in a candy production plant, Beaver Sweet Treats. And the process that they are looking at is the hydrolysis of sucrose to glucose-fructose mixture in acidic aqueous solution. So they're making the stuff that turns into those hard orange candies, right? And they're asked to evaluate whether to implement a new process which would allow for higher conversion but involve costly separation steps. So you can see the beginning of the task here to the right. It's written as an interoffice memo from Benito Beaver, who is the president of engineering at Beaver Sweet Treats. And it's, the subject is a process design recommendation. We are excited about our high volume, continuous manufacturing process design for our new orange candy product. This process will produce glucose, is the chemical signature for glucose, fructose, via hydrolysis of sucrose in aqueous solution. These higher volumes will reduce cost and energy use. Your team will be responsible for final process design and setup. And then it asks them to do some specific things. It asks them to start by sharing ideas on how best to work together as a team. They've never done this. This is week 7. They may have done this someplace else, but they've not done it in this class at least. Then they are to sketch, as a group, fully labeled process flow diagrams comparing the current design with one that utilizes the new additive. So they're trying to understand what the process looks like. Then they're supposed to brainstorm specific engineering questions that need to be answered. So they're not asked to solve a bunch of equations. What they're asked to do is think about what do we need to know and how are we going to design experiments to find out the answers to these questions in order to make this decision. And at the end it says, and the fourth thing is to provide me with any feedback you might have on my ethical approach to investigating this opportunity, which was an idea his niece had about how to improve their candy production process. That was a cool idea. So are there any ethical problems with my niece's idea, is basically what they're asked to do. So it's really different from what they've seen before. So there were 4 episodes. I'm going to show you a bit of 3 of them. The first was just the introduction and framing by the GTAs. I'm not going to show you that. It was basically just walked them through the handout. Didn't explain any of the bullets particularly. And then there's a little bit of the teaming norms episode, and then a transition clip between the flow diagrams and the final episode called Where Does the HCl Go? So I'm going to get ready to turn and talk because I'm going to ask you to look for some things and then chat with each other a little bit in the video. All right, so I'm going to show you the video on teaming norms. I want you to look for participation or talk time. Was it dominated? Was it distributed? What do you see? Do they seem confused? And if so, about what? And do you think that this is, if they're operating as if they are engineers, or are they operating as if they are students? Okay? All right. So it's a little clunky because of the way we've got the video set up. Nope. Get big.
First bullet point. Can I read this on that word next to this? But it says address every bullet.
Yeah, so you could talk about as a team like on this assignment, but you could also talk about maybe if you were dividing, like once you get down to this ball, you can talk about the tests, you could kind of provide a way to like share that.
Okay. So turn and talk to a neighbor. What did you see? Were they confused, and what about? And were they in school world or engineering world?
I realize that. They say showers are very bad.
Yeah, it's going to right.
Okay. So what did you see? You saw confusion. Yes, they were confused. What were they confused about? Say it again? Yeah, what was expected of them? Okay, what say more?
No right answer here. There's no question mark.
There's no question mark. Yeah. So where did they look for information about that? Where was the authority in this task, as it was enacted by them? Yeah, it's like it doesn't say that. And did you notice how they oriented to the TA who was doing the explanation? And if you know, I didn't see this actually until last night when I was looking at this, but there's another group or two that are nearby that are also like leaning in, trying to hear what the TA is telling them because they're all confused about this. All right, engineering world or school world? They're in school world. All right. So I don't want to take a ton of time on this because that is, yes, it is confusion, but it's school world confusion. Did you notice anything about the participation or talk time? Anybody? Two males talk. Well, the first person to talk was the female. That's we call her F1 fondly, female one. Yeah. All right. First bullet point, right? That's F1. Yeah, but it wasn't really even. It wasn't totally dominated by one or two people, but there wasn't a lot of participation by everybody else. So, all right, let's go on. So the next part, they're going to do flow diagrams. So this is the part, draw out a labeled flow diagram for the processes. And so I'm going to show you. Oops, I put my computer to sleep. Sorry. I'm going to show you the next clip, and we'll hope that it works as well. Oh, look for the same things. Participation. Are they confused? If so, what about? Is it school world or engineering world?
So is that
Well, I think so. It doesn't.
I don't think it's that.
It only has a conversion of 20%. It doesn't say that the rest of it comes out as the aqueous solution of acid and base, right? Because I think it's the unreacted sucrose, right? The unreacted sucrose, it's like the same thing. It's like the same. Right.
So it's just like the acids like the powders.
All right. So, turn and talk. Was it dominated or distributed talk time? Was there any confusion? If so, about what? And were they in engineering world or school world? Go.
They're still confused on the assignment. We're still trying to answer the question on the worksheet. F1 and M2 definitely.
Yes. They even said C maybe a little bit more, I think, because F2 is actually yeah, they seem to want more information.
I think that it is, these kids are stuck in school.
Right, yeah.
The kids are stuck in this. So they get confused because the assignment is not given to them like the way it used to be, right? So they're confused not about the phenomenon. They're confused about the assignment. It's a totally different thing. They're confused about like what's expected.
Yeah, I mean, I think they were sorry for this. Can we do this without doing this? Sort of stuff where we need that. I mean, I don't think there's more code to be done. I think we need
Okay.
We should get some videos.
Okay, let's get back together. I still have another clip to show. So quickly, what did you notice about in that videotape? What jumped out at you?
They were each drawing their separate diagrams instead of working as a group. Everybody was sketching their own.
Yeah, they were all, if you look at the 6 of them around, they are all kind of oriented towards their own worksheet. Yeah.
I have a question about that. Are they being graded based on their individual work they turn in? Like what I write down on my paper is my grade for this, not the group gets a single grade based on whatever?
That is an excellent. That is an excellent question to ask. So how would that affect things? Do you think?
Well, so in my experience, when you give one worksheet to 3 people, they're constantly grabbing with each other, looking at it, making sure that whatever they thought is somehow being influenced on the sheet. Versus there was 2 students in particular I noticed never even looked up to look at their peers who were talking. They were just doing their own thing. So they saw no value in contributing to the presentation. I'm not surprised.
Right, or possibly they heard the talk as narration to what they were doing themselves on the thing. So maybe there wasn't anything to question or engage. Yeah, I don't know. That's an excellent question. What else did you notice or wonder about? Yeah.
They still wanted to focus on the coolness of the task because they're talking about whether certain things are given to them or not given to them, and so they dismiss the one girl's suggestion because they think it's not part of this school task rather than thinking about whether it should be something.
Right. Yeah. One of the things we're interested about in looking at these videos is when we see a switch from one world to another, what happens? How does that switch actually occur? So that part that you noticed there was the first bid to switch it into engineering world. It was not taken up.
But those kids are stuck in school world.
Yeah, I know.
That would be my explanation.
Totally.
It might not even be the task.
Yeah.
The kids are stuck definitely.
Yeah. Like this is what works, right? Yeah,
I
Nero.
was also thinking about the sort of the gender dynamics, kind of what I'm doing. Initially, when the first students go, I was expecting him to kind of dominate what's going to happen next, and then the first woman kind of came in, and then the sort of the discourse and the centralized talk is just centralized around her, and then she interacted with the second woman. I think I was based on sort of like I was wondering how the gender dynamics were sort of mapping onto or not the different worlds, right? Engineering world, school, or some other kind of bigger world might be playing out.
Yeah. Yes, we wonder the same thing. So we should talk about that. We don't have enough data for me to actually say things publicly, but we got notions about what might be going on there. All right. Any last contributions? All right. We're going to continue the same clip, and you're going to see maybe some differences, so watch for them. Same questions. So this is the episode called Where Does the HCl Go?
Into a product because separation recovers 95% of the reactor sucrose. And it only recovers 95% of the HCl.
Yeah, so it doesn't even talk about HCl.
It doesn't count.
It's separated.
So where does it go?
I just don't want to talk about sucrose, but I'm also talking about it. Because they say it's hydrolysis of sucrose in the aqueous solution. I think it is. Because I think the sucrose is the same thing as the acid. Yeah.
So that means you don't have acid and both blood sugars are separated. Because it tells us that the separator recovers 95% of the reacted sucrose and loses 5% of the glucose to the water, but it doesn't talk about the HCl at all.
Yeah. So would that be coming out with the glucose fructose part?
That's my question.
Well, so that means that 5% of the sucrose is coming out with it, right? So I think we kind of don't really have to worry about it, because I think it kind of is just with the sucrose. Give us some awareness of the solution. Let's just like throw us off.
Does that mean that there's still some stuff left? Well, so that means everything you and so is there like a little system for the edit? It's just as soon as right when it's ready.
Because they say only 95%. Yeah.
Because it's taking and it's taking protons when it breaks, there's this oxygen in it. This is alcohol. Which would be like this oxygen. You just assume that
I mean, it must be. I mean, if it's coming out of the reactor, it has to be with the final product. We could maybe say that it doesn't enter the reactor, but I don't think we would say that. You know, I think it wouldn't just hang out in the reactor on its own.
yeah, that's weird. Okay. So it's like two mixing points along the loose pin.
Okay, so turn and talk. What'd you see?
So I think I have eventually M2 gets It's just a nice little part that I don't see dynamic. Right. I think you're we don't have support for this, we never heard Bob didn't respond. I could find an email like that. Well, that's not these guys did in NASA. They were on the equipment.
Okay. Okay, what did you see in this final episode that was an interesting pattern or a difference that you saw in the interaction, or yes?
There was a lot of confusion that in engineering world would have been easily resolved by consulting sources to find out what the reaction was.
Yeah.
Because they obviously didn't know.
Mm-hmm.
But nobody was access to the resources.
Right.
On their phone.
Yes. And interestingly enough, we've had this conversation about that kind of interaction with that kind of, well, in an engineering, in a fab, they'd be able to go to so-and-so and they'd be able to do this. The question is, do you want them to have easy access to that resource and get the solution quickly, or do you want them to actually have to think about what they're trying to find out about? So that the purpose, the way you do engineering world in, as Joe says, school world, because they are in school world, may not be quite the same as engineering. So that's a way in which that might be. Tiffany, you want to follow that on?
I did. So, they're hung up on a very trivial aspect
Mm-hmm.
of a minor thing that has to do with the whole problem.
Mm-hmm.
And yet they're actually, it's unlikely that they will reason their way through this because they don't have enough discipline to understand
Mm-hmm.
knowledge.
Mm-hmm.
So that goes to your point. Is it profitable at them? They're worrying this tiny point. They don't understand the role of intelligence.
Mm-hmm.
And so it's going to be very difficult for them to move forward until they get some knowledge.
Okay. Joe?
So let me just acknowledge on that. Okay.
I
But there was a switch from filling out the worksheet to figuring out the problem.
But they're not figuring out the problem.
They're trying to.
They're trying to, but
They're
they're not
lacking
going
some
to
background knowledge.
and they're
But the
stuck.
conversation changed. The conversation changed from, I gotta fill this out, when I'm worried about,
But if they can't figure it out,
Okay.
that's my point.
All right. Whoa. All right. I'm gonna be a traffic cop here. I heard something from the back of the room in response to that they haven't figured it out yet. Yes.
I was kind of comment on what Joe said, that even if they couldn't get you figure it out, even though it's a few times now, I still think there's some merit to it, and we're just still in college, and we do want them to figure eventually we wanted to figure out, it's still a step in the right direction. We're just kind of.
I don't think anybody's saying we don't want them to figure it out. I think what we're saying is, would it be more productive to have them figure out things that they can figure out?
Yeah,
I'm saying
well,
they took a step in the right direction.
Yeah. Okay. So what did you notice? I'm gonna shift this just a little bit. What did you notice about the interaction? Because I heard that come up in a comment too. How did that change over the course of that clip? Nero.
Over here.
Oh, sorry. You were.
Over here in the corner.
Whoop. Oh, there you are. Hi.
I thought
Sorry.
there was interesting things about the interactions, and that it seemed to be there be more dispersed talking. But I was also really interested in paying attention to whose ideas were taken up and whose were claimed. At one point, the man number one, I think he said like, "My question. That's my question."
That's my question, right?
Well,
Yeah.
it seemed like one of the women already had voiced that.
Right.
Question. So I was interested to see who needed to like validate those questions or those comments.
That is a pattern that we're starting to notice across groups, that when there's a failed bid by somebody who's not one of the leaders of the group to move it out of school world into engineering world, it often is resisted by the leaders until one of them, or and maybe it's another person, but it seems to be like one of the two main people that have been talking takes it up in whatever way, even if they claim the question for their own, then it then becomes a legitimate question to talk about. And once that happens, then you see the more dispersed kind of breaking it. They broke up into little pairs and they're showing each other their diagrams and they're trying to work it out. And it looked very different from the back and forth fill out the worksheet part. Right? Did you notice anything else that jumped out at you that you thought was curious or interesting?
Took a long time for them to get back to their yay.
Yeah, and to your point, what the TA says is, oh, you don't need to worry about that. And we went, oh, no, they were confused. It would have been a great time to push them a little farther and talk about at least why they don't have to worry about it. But he just says, oh, no, don't worry about that. That's just like, move on. Sigh. But so let's show you just a little data from our analysis. This is a talk time graph that our Ed Mycor developed, which was really helpful in us visualizing, because we kind of thought that it was more distributed at different points, so we didn't have anything that was quantitative that we could really look at for that. So each bar is 30 seconds. The different colors are different students. So there's the students on the side there, and you can see this is the teaming norms thing where they're kind of thrashing around a little bit at the beginning, and then it kind of breaks up into two main people who talk towards the end of that. That pattern mostly continues. Orange and blue are M2, who's the blonde guy across the circle, and F1, who's the girl with the kerchief. And the green is F3, who's the one who raises the question. And you can see here's a bid, nothing's taken up. Here's that bid again, it's not taken up. And then it finally is. And then you start to see the dispersed interaction in the last episode where they shift over. And actually I showed you, I broke the clip about here. So school world went on for a little bit longer and then they made that shift. So that's one way we've looked at this. We've also looked at, we've used some codes. We've looked at participation as either coded as either dominated or distributed. It's dominated when one or two students take up most of the airtime. It's basically a short way to say that. And distributed when it's more spread out. Who the authority is when we did the discourse analysis was the instructor in the first two episodes, and then the last one is more the student, where they're trying to figure it out until they go back to the instructor. And the TA, now we can find out what the right answer is, and they shift it back because they are confused. Milo came up with these labels for this. Milo Kresge, our colleague, inglorious confusion in the teaming norms thing, where they're just kind of going, whatever, put down whatever, it doesn't matter. Minimal confusion in the flow diagrams because that seemed to be clicking along as expected. And that's what probably looks productive and good to most secondary faculty members. It's like, oh yeah, they get it, they understand what they're supposed to do. Yeah, I'm a good teacher, yay. And then we call this glorious confusion, where it is in fact a trivial problem. Yes, you're right. But it is, as Joe points out, also a really good first step, that they're actually trying to figure out something and they're embracing the fact that they don't understand and they're not immediately. M2 does take a quick look around to see if the TA's in range right at the beginning, and seeing nothing, they just try to figure it out. And all of the students participate in that, which is something that we're trying to create a more inclusive environment where more people feel comfortable participating, and that, even if it's on a wild goose chase, is better than 2 people leading them on a wild goose chase and everybody else nodding their heads and writing down the answers. So there's a role, we argue, for confusion or uncertainty in inclusive environments. When students are uncertain how to approach a problem, space may open for alternative ideas, bringing in knowledge from outside the course or outside the chapter. She says, people can't ingest that, can they? That wasn't covered in their textbook or their lecture. This could possibly contribute to more inclusive environments that require multiple brains and perspectives to make progress. So this is, we take a lot of this thinking from the work for the long time work in complex instruction in mathematics. That when you give students group-worthy problems that are juicy, that have multiple entry points, that draw on multiple kinds of knowledge, you get better participation and more even participation. There's also a role for confusion or uncertainty in meaningful engineering work, we argue. And I was lucky enough a week or so ago to be in a little colloquium with Eve Mance, who presented her stuff on productive uncertainty. And we said, that's it! We've been calling it glorious confusion. This is a much better, less pejorative, maybe way to talk about it, productive uncertainty. And what she says is that there's productive uncertainty and then there's unproductive uncertainty. And so maybe I don't know how you divide that, but some uncertainty actually does prompt the thinking. I mean, the kind of thinking that they were doing in that episode, though possibly in pursuit of an unworthy goal, was they took them back to the system. They were trying to understand the physical system and how the candy was produced, which is something that they need to do when they approach a problem in real life. They've got to have an understanding of the system. In a real engineering setting, they would have that understanding already. These guys didn't have that, so they're trying to figure it out. And in doing that, they're trying to reason using these tools. So it's productive or unproductive, certainty or uncertainty. Eve said, she's done this a couple times with audiences where she's had them try to put things in those boxes for the last science investigation that they did. When was the uncertainty productive? When was it unproductive? When was certainty productive and when it wasn't unproductive, which I thought was interesting. And it also, this is also similar to what Pickering talks about when he talks about free and forced moves. So sometimes you've got forced moves that are driven by your knowledge of the underlying first principles, your knowledge of the system, your knowledge of the setting, your knowledge of whatever material balances stuff you've been learning. And sometimes you've got free moves where you can come at things from various angles, and that's how progress gets made in science and in engineering. And that it should be a combination of those things. So trying to design tasks maybe in which there's both certainty and uncertainty might be a way to get those free and forced moves. So I just thought about what might go in those boxes. Don't take this as anything but my musings, but Schwartz and Bransford and company talk about overzealous transfer. Maybe you read the piece some years ago on overzealous transfer, where you take knowledge that you've learned in one setting and you apply it without change to a new setting, and it doesn't work very well. And so perhaps when you have unproductive certainty, it's when you think you know what you're doing, but you really don't. Right? So, and we see that as something that happens. We've seen that in various studies of engineering students that Milo's been in charge of, where students know something. They know the basic knowledge that they need in order to approach something appropriately, and they don't see that they're supposed to apply it there. So they go at it in this weird kind of way. They just go, okay, well, let's solve it this way. And then somebody says, but wait a second, didn't we learn in thermo class that blah, blah, blah? And they all go, oh, yeah. Oh, yeah, I guess we should be using that knowledge here. When we gave these tasks to students in the lab study, where they weren't in a regular class, but they had taken the class, when they got dragged back to school world, it was often with somebody saying, we're not supposed to know that yet. Right? This is that class. It's a sophomore class. We're not supposed to know that, so we can't use that knowledge that we have to solve this problem. So it's this sequestered, siloed, only pay attention to the stuff that you're supposed to pay attention for this class and nothing else, which doesn't translate well into, maybe into the wild. So, all right, we've done this. You can stop now. Go down. There we are. So implications for revolutionary change. Radoff and Jaber and David Hammer talk about learning, that students need to learn to enjoy challenge and learn to enjoy uncertainty, and that kind of learning that could happen over an increasing diet of these kinds of open-ended problems is meta-affective. So you're feeling about feeling. You're learning to feel differently about uncertainty, which I thought was pretty interesting. That's just come out. But how do we increase the instructor's comfort with uncertainty? Because the instructors are also uncomfortable. And we don't know whether this kind of analysis that we're doing could help with that or not. If we show evidence of more equitable participation, would that be convincing? Would that help convince? If they consider the engagement to be more realistic, maybe this wasn't a good example of that, but maybe if we were able to do that more, would that be convincing? We don't know. We're asking a lot of people to shift the way they become good at teaching in a system that honors those kinds of values. So I just want to say thanks to colleagues, Milo Koretsky, Michelle Bothwell, Devlin Montfort, Susanna Davis, and Ed Mykor, who are the current Red Team, past members, Christine Kelly, Jim Sweeney, Shane Larona. And also, you can see the Oregon State CBEE Revolution website by just going to cbee.oregonstate.edu revolution. And thanks.
So we have roughly 15 minutes for a conversation. So if there are questions that you'd like to ask Susan, you have 15 minutes. What?
That's a farther he can turn. Yes.
So in helping students first think about their shift from doing more engineering and getting out of the school, how much did you preface any of this for the students, or it wasn't?
In that, it wasn't. You know, and that was part of it. You saw that in the initial clip that I showed you. They're going, what's this?
Yeah.
Right? Because there wasn't that framing. Yeah.
So do you think part of the resistance to stepping out of school can also be like the structure of school, and that you have individual grades and they know individually, so how do you help the students to step out of that?
Yeah, in fact, Milo uses 2.0 in his studio for thermodynamics. And what he noticed was students were getting really anxious and resistant because they couldn't get to the end to be able to hand in the product at the end, even though it was for like minuscule points. And he's talking to me about that. He says, yeah, they're getting really anxious and they don't want to do it because they take too long and they don't want to just wrestle with the stuff. I said, well, Milo, why are you making them hand anything in? So he went to using a single whiteboard, which gets them out of everybody's looking at the worksheet, their own copy of the worksheet. So one whiteboard out there, everybody gets a different color marker. And you have them use the whiteboard as scratch paper communication tool. And then you can walk around as a TA and look and see some of the thinking that's been happening and know more about whether or not you should intervene after you listen a little bit. But it also frees the students up from thinking there's a product. So you tell them, I'm interested in whether your group makes progress in their thinking over the course of this 50 minutes. You may not solve this issue, but I want to see you make some conceptual progress. And that changed the whole dynamic of what happened. So it was absolutely this structural piece of, He didn't change anything else. He just changed those two things. Yeah.
So has there been dissemination of this?
We're working. We're working on it. Yeah, we've talked at some conferences. We've got some conceptual-ish paper that is in press in Cognition and Instruction that we can share that with you. There's been some conference papers on it. The data that I showed today, plus more of our analysis, is going to be presented.
Are others in his department adopting?
That. Yes, it's leaking out slowly. I mean, we've done some concerted efforts. We had a week-long workshop for faculty to develop Studio 2.0 tasks to use in their classes, which involved us trying to help them understand why they might want to do that and spend the time to do it, which was more or less successful. And all of them committed to doing at least one in their next course and getting their foot in the door. What it seems to be happening is the other faculty have taken this up, and the ones who've taken them up usually start with one or two and see that they really like the kind of thinking that students are doing, and then they do more. But you can't ask somebody to commit. It's a big task to create them for your whole class. And so it's a gradual kind of a take-up. So we're seeing maybe not as much movement as we'd like, and that's partly why we're trying to see if we do some analysis on the actual thinking and interaction stuff that's involved in this, that it might convince more people to take it up. And that'll help us too in terms of seeing what kind of effects it might have. Yeah?
So that's sort of, I guess, a long-winded question, but I'm an engineer, and so I believe in data and data-driven sort of adaptation of things. And I guess my question is, where is this really headed? How are you going to know if it works? Because we've had the conversation last night that undergraduate engineering is not teaching people how to be engineers. It's teaching them how to pass the fundamentals of engineering exam, so that after they have 5 years of professional experience, they can actually take the professional engineering exam. They can actually then be an engineer and they can sign off on drawings and diagrams and stuff like that. So if that really is the case, I mean, that's my hypothesis, that we're really teaching them how to pass the fundamental engineering exam. I think, to know if this works, my perspective would be you have to show that the students who have been through this versus a control group actually do better on the fundamentals of engineering. So,
right.
But you could clearly have a different vision. So how will you know, that this is better than what we do now?
Yeah, that's the, I'm trying to find my diagram here. That's the gold standard. So, well, really, yeah, this probably. Hang on a second. No, that's not what I want. Trouble is I can't see. Put your glasses on, Nolan. Okay. Oh. Well, it made the, yeah, I know, it's awful, isn't it? It changed the resolution to the point where I can't actually see anything. So we think about it as an activity system for a reason. We can't, if we're going to try to affect change in any component of the system, we've got to try to affect change in multiple components, or it's not going to have any impact. So, by now we've got these various things going on, and Studio 2.0 is just a piece of that. And so, yes, if we could get an experiment where we assigned half of the sections to Studio 2.0 tasks for the whole quarter and half of the students to Studio 1.0 tasks for the whole quarter, we could answer that question. The difficulty of actually doing that data collection in an actual live setting is astronomical, because if you are bought into the 2.0 model because you've seen it work in your own class to the point where you've developed 10 weeks of activities, are you going to then not allow half of your studio students to have access to that? They've only got one course in each of these courses. There's one course and there's a whole bunch of studios. So the only way you could do it is to have some of the students in the same course get 1.0 and some from 2.0. We would never get that past IRB.
Well, that would be the best way to do it. But
Yeah, exactly.
You could also just look at the data as a function of time. You know,
Right, and so, right. So we've been collecting some student response data in Milo's course where he actually is doing this over time, and it is early in their experience with Studio 2.0. So his is the spring of sophomore year, and they haven't had very many of these by the time they get to him. So we'll be able to do those analyses, but
I'm not an advocate of asking the students whether or not this is better or not. I mean, I'm an advocate of real data with measurable outcomes.
Yeah.
And so, like the right way to evaluate teaching is how well the students do in later classes, not how good did they feel about what happened to them in a particular class. Which is why I'm arguing for tracking something like the fundamentals of engineering exam, which in some ways is
and I in essence agree with you. The logistics of doing that in a live system we haven't been able to figure out how to do it. If you've got ideas about how to do that, I'd love to talk to you afterwards about those. That's the kind of process that we use in another context, in another big, huge revolutionary change that I was involved in. And we did have a licensure exam that was reflective of the things that we were hoping to accomplish. And so we used that in this DVR kind of way to look at improvement over time. So yeah, I agree. Yes?
I am still complaining about the design. And when you introduced the problem, I was first thinking like, oh, okay, the great challenge would be think how you separate the leftovers with the sucrose and HCl that didn't react. And the reaction didn't come to completion, which is what happened. And fructose and glucose, how do you separate it? And like this, in my head, that was the engineering challenge, right? But they didn't get to it because they were stuck in the
yeah.
To understand the science, and I was wondering at all if at that point until where you show us it was actually about engineering, and whether if they had the scientific knowledge, I don't know whether they have a little bit of stoichiometry, they know what is glucosidic bond, whatever. Where then it could be more true or more authentic engineering.
Right. Yeah. There's always a risk in showing a single task as your evidence because all of the flaws in that task become reasons to dismiss the notion in its entirety. So luckily we have other things other data that I didn't talk about that get at. So our lab studies, for example, were students who were doing a task from a class that they had taken and passed. So they had the background knowledge to be able to approach the task. And so that was a little bit, they didn't struggle with the same kind of points that if they knew what they were doing, they wouldn't have gone in that direction. And so that's an issue. But we still think this is an interesting case of when they do start trying to figure it out together as opposed to just approach it algorithmically and efficiently, the participation shifts in ways that we think are productive. That they actually do try to reason it through with the system and what they do know, even if what they do know is incomplete. But if I was going to use this task, again, in a class, and I had seen this video, then I would know something about how do I need to redesign the task to more get at what we were trying to get at. And really, what he really wanted them to do was that part that they didn't even get to in the task because they got so bound up in this one thing that was this ethical issue. And he did want him to talk about ethics, but he wasn't even thinking about that when he designed the task. So that was why we encourage people to look at how students, I mean, we do this in instructional design all the time. You design a task and you say, okay, well, what did the students do with this task? And can we learn something from what they did with this task that will help us in designing things in the future? So that wasn't the focus of this talk, and so I didn't really talk about it. But yes, I agree, totally. Yeah, I know, I was like, oh God, why did they do that? But then isn't it kind of cool that they did it? So, and we see similar kinds of productive uncertainty things happening with much more competent students in tasks that are better suited to them. Competent being that there's a match between the task and the student and what they do. But I'm also reminded of Randy Engel's argument that you have to balance problematizing the content with providing the resources that students need to be able to attack the problem. And in this case, we had problematized the content in a way that we didn't anticipate. And the students didn't have the resources that they needed to attack it. Right? So. Yes, I agree. Yes?
I was wondering, thinking about that slide presented with the matrix of productive, unproductive certainty and uncertainty, I was wondering if you've been able to look back in maybe studios or classes that have been able to do multiple Studio 2.0 tasks, and if there was a difference in maybe students third time doing a task like that versus their first time, and their willingness, their ability to get into that productive uncertainty quicker.
Yeah, that's what we're trying to collect some data on that, and we have very few instances of entire courses that are largely or mostly this kind of task to be able to do that longitudinal analysis. But we're getting the video in the can as we speak, to be able to do some of those. And what we see, and what instructors' impressions are that spend time in their studio sections, we did in all of them, is that students do become more comfortable over time with this kind of task. And by the end of the course, and TAs tell us this as well, that it's very nervous making at the beginning when they run into these tasks. They're not sure what's expected and what the instructor wants and all this kind of stuff. But once they get a little bit more comfortable with the approach, then they actually dig in better and better. We see this, this kind of approach has been used in the capstone course for a long time. So in the capstone course there, they do a virtual vapor deposition reactor project where there's a piece of software that mimics a vapor deposition fab, and one that's a bioreactor that's analogous. And it behaves like real reactors, and the students have to come up with a recipe for making silicon wafers that produces a silicon wafer of particular specs, but also meets the engineering objectives of controlling costs and so forth. And so that's something that Milo invented and has published a number of articles on. But it's really fun to analyze the actual discourse of those students doing those problems, because they start out trying to attack it kind of like a school problem. And then once they slip into, usually it's somewhere around the time they get either feedback from the instructor that the little ideas they had about doing it as real engineers were actually okay, or they get their first data set back that they have to make sense of. Because they put in their input parameters, they push the button, the thing says, okay, here are your wafers. They decide where to measure it and how many times, and they get their data back, and they have to make sense of why their chips aren't even and what that might be due to. And then then all of the groups that we've got tape of start trying to figure that out and reason through it in ways that we want to see them do. But we don't want to wait till capstone to let them do that.
So I'm going to put this to an end and thank Susan once again.
Thank you.
As always, we have a little
Thanks.
present for Susan.
Thank you.